All right, let's go to this. All right, here we go. Okay, so development lens, what is development lens, right? We need to understand that. So first thing first, we need to understand the definition of development lens. Okay, now the definition of development lens means that it's a, so let me just put out here, it's the lens of bars required to be embedded inside concrete. Okay, to be embedded inside concrete that will develop sufficient stresses in a bar. Okay, that is the definition of development lens. Okay, to put it more visually, so I just want to draw a figure here. So say I have a concrete, right? Concrete beams. Okay, and now we all talk about the flexure reinforcement. Now you've seen that usually at the end of the cages, okay, usually at the end of cages, it is bended like that. So you have a certain length of the reinforcement, certain length of the reinforcement. So we assume that during this length, now the stress, right? When you're trying to pull the bar, right? So the concrete has to provide enough bound stress, means shear stress, transfer to the bar, that just at the end of the bar, the stress in the bar can reach the yield strength of the bar Fy, to yield strength of the bar Fy. Okay, so that's the upshot of it. Okay, that's the upshot of it. So it's just sufficient length of the bars that you can develop enough stress in a bar to yield it. Okay, so this is the definition of development length. Okay, and we'll go into detail about it right after this, but let's quickly talk about the types of them, right? So in terms of development length, we have development length in tension. Okay, this is definitely in tension because at the bottom of the beam, and we have development length in compression. Okay, and we also have a development for hooked bars. Okay, so these are different scenarios. Well, we mainly focus on the development length in tension in this lecture. Okay, so this is what we're going to mainly focus on. Okay, it's the tension bars we're going to focus on. All right, so there are two learning objectives today. Okay, two learning objectives. So learning objectives. The first one is understand the definition of it. Now we'll just briefly talk about it and then elaborate in detail, okay? Understand the definition of development length. Okay, and the second is know how to calculate it. Know how to calculate it. Okay, just want to use the shortcut here. Development length, okay, development length. All right, so this is our objective. So let's take a look at the definition of it. So if we're going to talk about definition, we have to start with another basic concept. So first definition of development length. Okay, and the basic definition comes from, bonding between concrete and steel. Okay, between concrete and steel. Okay, so what is bonding? What is bonding, right? So bonding means I have rebar and I have concrete surround it, and they're together. They're together, right? If I draw a drawing to show that, say these are my rebars and I have ribs sticking out, and I have another rib sticking out, and then I have another rib sticking out, and these are my rebar. So on the other side, I have the same scenario, same scenario, same scenario, like that. All right, so these are the geometry of the rebars, okay? Now, considering this rebar is buried inside the concrete, right? So buried inside the concrete, okay? I'm just gonna use some symbol to show that these are aggregates, mortars, these are concrete. And now I want to pull the rebar out, okay? Because the rebar is sustaining in tension, right? So assume I'm gonna pull the rebar out in terms of force P here. Okay, so in your mind, think about when I mobilize the bar towards the right direction, right? I will certainly meet the resistance. I will certainly meet the resistance from the concrete, So the first type of resistance I see is the bearing on the ribs, right? So the concrete will push against this rib and prevent it from going, right? And the second type of, right, it's just everywhere, right? So this is the first type. Let me just label them all. Okay, so these are the bearing forces from the concrete, right? From concrete. Now the second type of it is the bonding stress, shear stress that is on the bar and against the pulling direction, right? These blue ones. And these are the chemical adhesion. Chemical adhesion, essentially just the adhesion between the bar and the concrete. Adhesion between the bar and the concrete. And on top of it, right, we also have friction, right? Or we call it aggregate interlocking, right? Friction or aggregate interlocking, the purple color here, also in a parallel direction. So these three type of forces or resistance from the concrete constitute the bonding stress between the bar and concrete, between the bar and the concrete. So we can say that the bond stress, the bond is contributed from these factors, right? From the following factors. Excuse me, any questions? Okay, all right. Sorry, I just have to mute you short. If you don't have a question, if you have a question, you can just speak out and or raise your hand, okay? Or else I have some echo here, okay? So the bond is contributed from the three factors, from the following factors, right? So we talk about this one, take a different color. So one is bearing, okay? Bearing, right? Of deformations of the bar. Deformation means the ribs on the bars against concrete, okay? Bearing against the concrete, okay? The second is the chemical adhesion, right? Use different color to match. So second is chemical adhesion. Well, they're parallel, so I can mix them, okay? Chemical adhesion. And the third, blue one, is the friction. All right, so these are the three different factors that give you the resistance between the concrete and steel, between the concrete and steel. All right, so very important assumption here though, very important assumption here. In RC design, right, in RC design, well, in research is a different story, but in RC design, we assume no slip. What does this word mean, right? What does this mean, no slip? No slip means there's no relative deformation between the bar and concrete. They're together, okay? So this is very important, okay? meaning that the resistance paths between the bars and concrete are fully transferred. There are no stresses lost. Okay, there's no stresses lost. Hence, no slip, no slip. All right, so this is the bond stress. This is the bond stress. Okay, so now if this is the bond stress, I imagine I have a situation, for example, I have a column, this is the column, and I have a beam, right? Cantilever beam and column join here. Cantilever beam and column join here. Now assume I have a pushing down force, right? A bending moment caused in the negative direction that pulling the bars in the beam in the tension, right? So this is the bar in the beam in tension. Okay, and let's assume the bar is straight. So easily you can conceive that if I pull this way, if I push it down and cause a bending, basically I'm pulling the bar this way. If I don't embed the bar deep enough into the column, what will happen? The bar will just simply slip, right? Got removed from the column, or we call it pull-out failure, right? So possible bar pull-out. Okay, if L development length is insufficient. If I don't have enough length to carry those growth of bond stresses, right? So you can imagine from here in and goes all the way here, right? As you go away closer to the pulling force, I accumulate more stresses along the interface. I accumulate more stress along the interface. So if I don't have enough length, I may get the bar pull out. I may pull the bar out. All right. Hence, the development length, definition of development length, so L development length, okay, is the length required, okay, is the length required, okay, length required to ensure enough tensile stress can be developed in the bar to reach the yield strength, okay, to reach Fy. Very important, okay? So you can just think about it, it's just enough length that accumulates stress enough to yield the bar, All right, so that's the simple definition of it, okay? And this development length can be calculated, And ACI provide a basic equation for it as well. So basic equation for development length is given by ACI, okay, 25.4.2.16, okay, and also 25 in general, 0.4, 0.2, 0.3, okay, and I'll explain why I have two places, right? But from this place, what you see here is this equation, right? So the equation says LD, just going to use the shorter, right? LD developments equal to 3 divided by 40 lambda, and you know lambda is the weight coefficient, right? Normal weight is 1.0, light weight is 0.75, and Fy is the yield strength, and square root of F prime C, okay? And then multiply coefficient of phi t, okay? And we'll talk about it, okay? We'll talk about phi t, all right? And another coefficient phi e, okay? And another coefficient phi s. So 3 coefficient multiplied together divided by a CB, which is the coefficient related to the concrete cover, and KTR, which is coefficient related to the confinement, divided by dB, bar diameter, okay? And this fellow here is together, okay, at the bottom here. And this 3 multiply dB, which is the bar diameter, and has to ensure that this is bigger or equal than 12 inches by code, okay? And remind you that this is on 14, okay? This is code 14. Okay? And then when we have another requirement saying when you want to use this equation, okay, you need to ensure this coefficient at the bottom here, CB plus KTR divided by DB, this whole thing has to be smaller or equal than 2.5. Smaller and equal than 2.5. And if you feel confused, right, what's this, right? What's this? You can simply understand this factor as a confinement factor or confinement effect. Okay, and what I talk about, what is confinement effect? I talk about confinement effect. Okay, now these are complete equations. So let's take a look at each parameter, right? So LD, needless to say, this is defined as development length. Okay, this is defined as development length, and it's always in the unit of inches. Okay, dB, we all know that is bar diameter, and of course it's in the unit of inches as well. Lambda, we know that normal weight concrete is 0.1. Okay, lightweight concrete it is 0.75. Okay, so these are the big coefficient, right? Now let's talk about the smaller ones, right? First of all, CB. What is CB? CB turned out is a concrete coefficient, concrete cover coefficient, right? So this is about the concrete cover. This is about concrete cover. And it is smaller of, okay, smaller of these numbers. First, we call it C1, okay? And C1 is a smaller of CX, oh, sorry, CX, CY. You're more confused. But this is only the first one. Where is the CX? Where is C1 coming from, right? So to help you understand, let's draw a figure here. So if my bar is right here, this is rebar, okay? I'm joining cross section, and this is my edge of the, sorry, this is the edge of the concrete. All right, so CX is the distance between the horizontal edge to the center of the bar, and CY is the distance between the center of the bar to the bottom surface of the concrete. Okay, so C1 essentially is the distance, the shortest distance between bar center to concrete surfaces. Okay, bar center to concrete surfaces. And this is only the first term, okay? Now, there are a second term, which is C2, right? Now, C2 is what? C2 is defined as half CC, right? What is half CC? Half CC is, if I have a bar here, and this is my, this is my concrete sections. CC is the clear spacing between the bottom edge of the bar to the bottom surface of the concrete section, okay? So this is that, so it means half of that, okay? So CB, which is the concrete cover related coefficient, is the smaller of these two, is the smaller value of these two, okay? Now, this is the corner here, this is the corner here. So what if I'm in the middle, right? So if I have bars, sorry, here. Okay, so if we're talking about the corner bars, fine. How about we talk about the bars in the center here, right? In the bar of center here, I only have CY. I don't have a CX. Okay, the same thing here, if I'm talking about the bars in the middle, so this is the corner bar, and this is the bar in the middle. Now, to talk about this, CC has to be the shortest between this or this. Okay, so shortest between the bars or between the bar and the concrete surface. Okay, so these are the coefficient regarding to the concrete cover, coefficient regarding concrete cover. All right, so moving on next, KTR. Okay, so KTR we talk about is part of the confining factor, and it's essentially defined as transverse. Essentially defined as transverse reinforcement factor. Okay, transverse reinforcement factor. Okay, so in the short term, this is representing the stirrups. And the equation for it is 40 ATR is the cross-section area of the transverse reinforcement stirrups, and divided by spacing of the stirrups and number of bars being splitted. Number of bar being splitted. Okay, so these again need to explain, right? Need to be explained. So let me just put these numbers here. So these are the stirrup spacing. Okay, and ATR is the stirrups area. And this is legs. Okay, this is no, sorry, not number of legs. This is number of bar being developed. Number of bars being developed. Okay. Okay, so let me show you the cross section, right? Show you the cross section. So this scenario represents if I have a beam like this, and I'm looking at the cross section right here. Okay, now assume I have 4 bars crossing the beam, So longitudinal, this is 1 bar, 2 bar, 3 bar, 4 bars. Okay, and I'm gonna go a little bit crazy. I say, okay, look, I want to have 2 stirrups, which means 4 legs developed. So I'm gonna draw a stirrups this way. It's gonna go to this bar here, going up, and then go around it like that. Okay, and I say this is not enough. I need another stirrup, so I need another stirrup going on this way. Okay, my drawings is still horrible, but you get the gist. Okay, so now I have 4 legs going across it. Okay, so the area, total area of these 4 legs that are across this section is called ATR, area of the transverse reinforcement. Area of the transverse reinforcement. Now, this is a side view, right? So from the 3-dimensional view, right? I have 1 bar, 2 bar, 3 bar, 4 bar, right? Developed this way, and I have stirrups going like this. Stirrups going like this, okay? And I have another one going like this, and going like that, okay? So the spacing is this as here, right? As the spacing. Now, the only thing that remaining is n. What is n? Now, I have 1 bar, 2 bar, 3 bar, 4 bar that in the longitudinal directions being developed. So this is called 4 rebar being developed. Okay, 4 rebar being developed. Okay, so let's take a look at this equation again. So the larger the area it is, the higher the confinement you have. Okay, and the more bars need to be developed, the average of confinement effect is lower. Okay, so this is something you have to keep in mind. Okay, keep in mind. So more stirrups means better bonding. Okay, more stirrups means better bonding. All right, so now I have explained the parameter regarding to the confining effect. Okay, and you know lambda Fy squared root F prime C, and you know dB. The only thing that we haven't talked about is what is this factor here? Phi T, Phi E, Phi S. Okay, so let me just quickly put a note here so you can see immediately. So Phi T is about bar location. Phi E is about coating. Okay, and Phi S is about the bar size. All right, so how so? Let me explain, right? Let me explain. So for first of all, phi t, right? What is bar location, right? So phi t, let me use black color here. Phi t is a bar location factor. Phi t is a bar location factor. All right, so what it is that, excuse me, phi t will equal to 1.3 if more than 12 inch of concrete, 12 inch of concrete, okay, placed beneath it, the bar. Okay, meaning if I have poured a beam, right? If I poured a beam, so this is a different color. So if I have a concrete beam like this, and if I pour the beam upside down and my reinforcement has more than 12-inch concrete underneath it, now I have a solid bonding. I have a solid bonding. Hence, it is 1.3. Okay, but if I don't have that, if I pour the other way, normal way, Pht is just 1.0. Okay. Okay. So if I just pour it other way, I have a very small concrete cover underneath it. I'm not sure about the quality of the concrete, so that's going down, right? That's going down. Now, Phe is the coating factor. Okay, Phe is the coating factor. Now, what is coating? So if you go on the highway, there are green color bars, right? Green color bars, and there's dark color bars. The dark ones means bare, there's no coating. Okay, so when there's no coating, Phe equal to 1.0. Okay, uncoated. No coating, bare bar. Okay, and if you see green color bar, okay, Phe has to be 1.5. Phe has to be 1.5, and this is epoxy coated bar. Okay, epoxy coated bar. Okay, and this has another criterion with concrete cover. Okay, with concrete cover bigger than 3 dB. Bigger than 3 dB, or clear spacing means between bars, right? Has to be big, smaller than 6 dB. Okay, and if you have other cases other than this, but still epoxy coated case, you have 1.2. Meaning that with coating, especially epoxy coating, you need a longer development length. You need a longer development length. Okay. All right. So this is the coating effect. This is the coating effect. Okay. Last but not least, the bar size effect. The bar size effect, Phes, right? Okay. So bar size effect means if I have a bigger bar, I need to worry about the reduction of bond strength. Okay. So for smaller bars or numbers, for example, number 6 or smaller, okay, I have a 0.8, 80%, right, of development length. Okay. Now, if I have number 7 or bigger, number 7 or larger, okay, Phes equal to a 1.0, right? So it's just normal. It's normal. Okay. Now this is our development length equation, and these are all the parameters. These are all the parameters. So you can see that it's pretty long. It is pretty long, right? And you have to really investigate the detailed situation to determine what are the coefficient and what are the factors that has to be taken into consideration in calculating the development length. All right. So this is rather lengthy process. Sometimes in the field, you don't have time to go through all the details. And sometimes you simply don't have all the details. All right. So now in this case, ACI also presented a simplified approach. ACI also presented a simplified approach. Okay. Meaning you don't have to use all these complicated things. You can use a simplified approach. Okay. So let me present the simplified approach. Okay. And we're focusing on mainly on the tension development length. Okay, tension side of it. Tension development length. Okay. So in the simplified case, the equations were divided by 2 factors. One is the spacing, bar spacing and cover, right? So spacing and cover. Okay, in the X column, and the other is bar size. So number 6 or smaller, and number 7 or larger. Okay, once you made this division, I can simply divide my development lens cases into two categories, two scenarios. All right, two categories or two scenarios. Okay, so in category one, right? So I call it case one. Okay, 1.1. That is when the clear spacing is bigger than 1 times bar diameter, or clear cover is bigger than 1 times diameter, plus, right, the stirrups are ties, they're connected, okay? And the second subcategory is clear spacing, okay? Clear spacing bigger than 2 times of diameter of the bars, or clear cover bigger than 2 times of diameter of the bars. All right, now in this big category here, if you have number 6 bars or smaller, you use different equation. This equation is Fy, okay? T, you still use that factors defined earlier, divided by 25 lambda square root F prime C, okay? And bracket multiply dB. All right, if it's number 7 or larger, you have Fy, T, E divided by 20 lambda square root of F prime C bracket dB. Okay, so you say, Bob, this looks same as previous equation. What are you talking about, right? What do you mean by simplify? Now I want you to pay attention. You see here in this equation, there's no concrete cover and there's no KTR, transverse reinforcement, anymore. So the whole idea of simplified equation is to get rid of this confinement effect. Okay. All right, so that's why it's called simplified approach. Now you don't have to consider that. Okay, all right. So this is the first case, and all the other scenarios are defined as case 2. Okay, and in that you have equation 3 Fy phi t phi e divided by a 50 lambda square root F prime C and bracket dB. Okay, same thing here, 3 Fy, okay, phi t phi e divided by 40 lambda square root F prime C and dB. Okay, dB. All right. So this is the simplified approach, and you can find this. From ACI table 25.4.2.2, and this is 14. Okay, and I explain the difference between 14 and 19 later. Okay, but this is the simplified approach. All right. Okay. So there are something you have to remember, right? Something you have to be careful. All this, right? All this still has to satisfy some confinement conditions. To be satisfied. Meaning that if you want to use it, right? If you want to use it, you have to satisfy in case 1, you have to satisfy that the confinement factor CB KTR divided by dB is bigger than 1.5. And for case 2, you have CB plus KTR divided by dB is bigger than 1.0. These two categories has to be satisfied. Okay. Now, if you don't have these criteria satisfied, you cannot use the simplified approach. Okay. All right. So today is more conceptual. Just want to introduce you the concept and equations. So I think this is a good point to stop. I'm just going to stop here, and we'll go into an example tomorrow. Okay. So if you guys have any questions, please ask, and I'll stay behind. If you have other unrelated questions, okay, I can answer that. Let's see a chat message. Psi. Oh, sorry. I think I made a mistake. Okay, should be psi. Okay, I always confuse with phi. Okay, should be psi. Okay, thank you for correcting me. Okay. Thank you for correcting me. Okay, it's trident. It's really trident looking symbol. Okay, this is back to my ancient college time. Always confused. Okay, sorry about that. Okay, all right. Anything else, guys? Folks, anything else?
Yeah, I have a question.
Yeah, go ahead.
If you scroll up to CC.
Sure. Hold on 1 second. Right here.
Yeah. So I know that we do the smaller of between the bars or the bottom of the bar to the bottom of the surface. Why don't we do the side of the bar to the side of the reinforced concrete?
Side of the bar to the side of reinforced concrete. You mean here? Is that right? Is that what you're saying? You mean here?
Yes, right there.
Yeah. So I probably missed it. Okay. You are just trying to find the smallest.
Gotcha.
Yeah.
Okay, I just wanted to make sure that I understood that. Thank
Sure,
you.
sure, sure. Yeah, sorry about that. Yeah, it's always the smallest. Okay, it's always the smallest. Now, yeah, I think in the scenario that you have bars in the corner and the bars in the middle, you just need to find the smallest and apply to all of them. Okay, apply to all of them just to be safe, because that's the smallest concrete cover. You need more length to develop to reach the yield strength, right? So you want to pick the smallest concrete cover.
Okay, that makes sense.
Yeah, good. Anything else?
And
Yes.
and then so for the CX CY up above, we don't consider CX in the middle ones.
Yeah, in the middle ones, you don't really consider CX and CY. And the reason behind it is that for this C2, this is essentially so-called a group effect. That means you have multiple bars. And this is more like corner bar effect. If I want to draw it, essentially, we're looking at a crack that can generate here, and can generate here, right? And here in this, essentially, we're worried about the crack can generate here, can generate here, can generate here, can generate here. So they're a little bit different. Okay, so yeah, there's some research, but you don't have to go in that depth. All you have to remember is that for this, this you don't have to worry about CX. Okay, for the middle bar, you don't have to worry about CX. For the bottom ones, you do. You'd have to worry about all the clear cover or spacing, clear spacings.
Okay, that sounds good. Thank you.
Yeah, sure, no problem. Yeah. Anything else, folks?
When did you say the homework was going to be posted?
Oh, it's going to be posted tomorrow right after I walk you through the example. And it's going to be due after Thanksgiving. So you have the whole Thanksgiving to work on it.
So it's going to be due like the week. So
Yeah,
not next week, but the following week.
the following week, whenever the Thanksgiving holiday is done. That's all. You guys need some time to regroup.
Okay.
Yeah.
Thanks, Bob.
Sure, no problem. Anything else, guys? Anything else?
I also missed like the first bit. Are the tests almost done graded or?
Oh, if you walk in late, I'm still grading the exam. I think there are a few that I was just trying to finalize. You should be able to see it either Friday the latest or Monday the latest. But definitely have it before you come back.
Okay, sounds
Yeah.
good. Thanks,
And
Bob.
no worries. And sorted out all the gradings. I don't see us have big issues. So you guys can have a good Thanksgiving for all I'm concerned. Okay. Anything else, guys? Daniel, you still good? Are you still good, Daniel?
Yep, excellent.
All right. Okay. Thanks. All right. Well, I'll see you tomorrow. Okay.
See you then.
Yeah. See you. Bye now.